This is the last topic for the exam for you, and we talk about matchings today, which is another example of mechanisms without money as voting was, and this is a way to decide about some outcome that has impact on all the collective, where all the members of the population have some preferences, right? You have to come up with one decision for in a particular situation, which is different from other decisions. I will remind you a little bit from matchings in graphs. I remember that you saw that everyone was familiar with basics of graph theory. So this is just a few notions that we will need. So what is a matching on the graph? A matching on the graph is just a subgraph where any edge does not share the same, any two edges do not share the common vertex. So no vertex is covered by more than one edge. It can be uncovered or covered by exactly one edge. So the degree of each vertex in a matching is exactly one time, or it is not one. Now the size of the matching is the number of edges in it. And if we look at this example, we have 8 nodes, some edges in there. You can tell that if you take any single edge, for instance 2 and 3, it would provide a matching, right? You can take more edges into matching, 2, 3, and 4, 8 also will provide a matching, or even more, 5, 7. You can have 3 edges in a matching, they do not share a vertex. Can we do more than that? Can we have 4 edges in a matching in this graph? No, why not? It's written over there, right? Well, we have 8 nodes. We have 8 nodes. So if we have 4 edges in the matching, we have to cover all the nodes, right? So that no nodes share, no 2 edges share a node. But look that nodes 1 and 2 can only be, or both of them can only be matched to 3. So either 1 gets matched or 2 gets matched. So we cannot match all of them, and that's why we cannot have 4 edges in the matching, right? So a matching. So this was the best we could do in terms of how many edges we could obtain in matching. Such a matching is called a maximum matching. So this is the largest possible size matching. Note that for a given graph, we can come up with several ways to find a maximum matching. Now, the matching number of the graph is actually the size of its maximum matching. Okay. So that's just a parameter characterization of the graph. And finally, we would say that a graph has a complete, or another term for the same thing, perfect matching if this matching covers all the nodes, right? So in our example, for instance, we didn't have a perfect matching, right? The maximum matching had 3 edges, it covered 6 nodes, and we had 8 of them in the graph, right? So no perfect matching was possible. The special family of graphs that in particular we will work with in terms of marriage problems and stable matchings are bipartite graphs. Those are graphs where you can divide all the nodes into 2 parts so that you only have edges from one part, from one subset of nodes to another one, and there are no edges between the nodes in the same subset of the graph. Okay? So that you can have 2 parts, and usually it's common to use the terms left and right side for these 2 subsets, and we will denote them by L and R, left and right. And we would say that a bipartite graph is balanced if the sizes of these 2 subsets are equal. Okay, so if we have the same number of nodes on the left-hand side and the same number of nodes on the right-hand side, the So assume we have such a graph, and if it is not balanced, then we can come up with the measure of how much the graph is disbalanced. So look at any subset of nodes of one of the sides, let's say the left-hand side, okay, and let n be the number of nodes on the right-hand side to which our given subset S is connected to. Is it clear what I mean? So if we have, so this is the left-hand side, this is the right-hand side, we have some nodes here. Edges. And I look, this is my subset S. Now I look to how many nodes on the right-hand side, these three nodes are connected. This goes to this one, that one, and this is connected also to this one. So n is 3 then. All right. Now we then say that the deficiency of this given set S is the difference between the size of S, which is 3 in this case, and the number of nodes it is connected to. So in our case it will be 3 minus 3, 0. Or if this number is negative, then the deficiency will be 0. So it's the maximum between this difference and 0. And then the left deficiency of the graph, dl, will be the maximum number of these deficiencies over all subsets of the left-hand side vertices, and in the same way we define the right deficiency of the graph. Okay. Let's take an example. We have a complete bipartite graph K32. I don't know if you I would suppose you are familiar with the notation, but just to remind you, KMN is the usual common notation for complete graphs, where M and N, bipartite complete graphs, where the left index is the number of nodes on the left-hand side, and the right index is the number of nodes on the right-hand side. Okay. So we have a graph, we have complete graph has all possible connections, all the nodes are connected between the two sides, right? It's a bipartite graph. So if we look now at the two first nodes, L1 and L2 on the left-hand side, let's find the deficiency of this graph, of this subset. Right? So these are two nodes, and they are connected to all the nodes on the right-hand side. For two of them, the deficiency is 0. 2 minus 2 will be 0. If we look at the whole set L, there are 3 nodes, and they are connected to all the nodes on the right-hand side, but there are only 2 of them. Right? So we have 3 minus 2. The deficiency of this set is 1. And if you look at all other subsets, they all will be only less. Their size will be less than 3. All of them will be connected to both nodes on the right-hand side, so we cannot get a larger deficiency than 1. Right? So the maximum deficiency will be 1, and this is the left deficiency of this graph. Okay, so this will be dl. What about the right deficiency? It's actually easy. Well, let's do it one by one, but then your answer will be immediate, in fact, because we have a complete graph and the right-hand side is smaller, its deficiency is 0. So look at the subset that contains one node, R1. It connects to 3 nodes on the left-hand side. So it's 1 minus 3, a negative number, the deficiency is 0, and it will be true for any subset because the smaller the size of that subset is smaller than all the nodes, than the number of nodes it's connected to, because all of them, 3 of them, and that's why the deficiency of the right deficiency is 0. And we have the following fact. It does require proof, which I'm not going to provide. It's a little bit long. It's not complicated, it's just a little long. But it's saying this, the following thing, that the matching number, and once again, what is the matching number? The matching number is the size of the maximum matching that we can find in the graph, as in a bipartite graph is equal to either the number of nodes on the left-hand side minus the left efficiency, and it must be the same as the size of the right-hand side minus the right efficiency. So in our example, we had 3 nodes on the left. The left efficiency was 1. 3 minus 1 is 2. The number of nodes on the right-hand side was 2. The efficiency was 0. 2 minus 0 is also 2. Okay, and that indeed is the maximum matching that we could find there, because on the right-hand side we have 2 nodes. Maximum we can match the 2 of them to someone on the left-hand side. Questions here? Another, this is in fact a special case of the statement that we just gave, and it's called the Hall's marriage theorem, that talks about perfect matchings in bipartite graphs. It was proven in 1935 by Philip Hall, and it's one of the central results in graph theory and matching theory. So suppose we have exactly n nodes on the left-hand side, we call them boys, and we have exactly n nodes on the right-hand side, we call them girls, and we want to answer the question whether there is a perfect matching in this graph. Now note that if we have not equal sizes of boys and girls, then obviously we cannot have a perfect matching. Right? We only can then, at best case, match fully the smallest subset of the nodes. So the graph must be balanced to have a perfect matching, but also it won't be guaranteed that a perfect matching exists. So now assume that each girl has some list of acceptable mates, so that's the guys that she likes, more or less. We do not distinguish at the moment. Is it more or less? They're just acceptable or not. All right, and we assume that the boys are real gentlemen, so none of them would reject any proposal if it comes up. So the first sentence, the girls have a list of acceptable mates, would be translated in a bipartite graph. So we build a bipartite graph where the boys are nodes on the left-hand side, or the right-hand side, whatever. Girls are the nodes on the other side. The preferences of the girls would give us an edge between a boy and a girl, right? And the boys being gentlemen would mean that this edge is undirected. Okay? So indeed we can translate this problem into a bipartite graph and find the maximal matching in this graph. So here we have that we see that first girl likes 3 boys, she doesn't like the 4th one, and so on, but the 4th one, in fact, is the most popular boy. He's liked by 3 girls. And Hall came up with the condition for the existence of a maximal matching. It is pretty intuitive, although I will repeat, the proof is pretty long. So the condition is as follows. So the condition says that every subset of R girls must be connected to at least R boys. Okay. So if you look at any subset on one side of size R, the number of links should be at least, not the number of links, the number of nodes on the other side that it is connected to should be at least R, at least its size. Okay? And this is for any Now, equivalent formulation of that, the deficiency of the left-hand side should be 0. And same for the right-hand side. Okay. We can, of course, rename boys and girls. It doesn't matter whether we start with the left-hand side or the right-hand side. And this condition only applies to the case where we have, once again, equal number of boys and girls, because otherwise the question about complete graph would not matter. So the graph must be balanced. And now we want to see how this condition relates to the existence of a maximum connection. Okay? So the condition only says how many connections each one of the subsets has, or what's the deficiency of every size. Now, it turns out that this condition is both necessary and sufficient for the existence of a complete matching in a graph. The necessary part is very easy to see. Okay? If the deficiency is not 0, then there will be unmatched nodes. Okay, so we cannot match them. The other side, the sufficiency, that's where the proof is wrong. So this condition holds for the graph if and only if there is a perfect matching in that graph. So if we look at this example again, this graph will not meet the Holt's condition. Look, for example, at the girls 3 and 4. They both paired with only one boy. Okay, so the size of that subgraph is 2. On the left-hand side, they're connected to the subset of boys of size 1. So 2 minus 1, the deficiency of this set is 1. So the right deficiency is at least 1. Okay, the condition does not hold. And of course, it's easy to see that a perfect matching does not exist because these two girls, only one of them can be matched to this guy, right? Not both of them. Because of this country. If we look at the left-hand side, we will see the same thing. Look at the set of the first 3 boys, B1, B2, B3. They all like the same 2 girls, G1 and G2. Okay, so the size of the set is 3. It's connected to only 2 girls on the right-hand side. 3 minus 2, the deficiency is 1. The left-hand side deficiency is at least 1. Again, there may not be a complete matching because these 3 girls cannot marry, these 3 boys cannot marry these 2 girls at the same time. A little bit sad. Look that indeed this was a special case of the statement that we had before in more general case for the matching number of graph. So this is the special case for the balanced graph where we have the same size of 2 subsets, left and right, which is n, and the deficiency of both was 0. And then we had that the perfect matching of size n does exist. A question before we proceed to stable matching. We all remember the simple algorithm for finding a maximal matching in the graph? Yes, no? Say something? No. Okay, that was fine. I'll show you one for the bipolar graphs. Again, it's simple. You look at, you take first node on the left-hand side. That's the graph. The idea is you start with some matching and then you improve it. So you take one node, you measure it somewhere. So you take this edge to the matching. Match. Next one. Can we match him? No, leave it. This one, can we match him? Yes. Take this one. This one, can we match him? Next one, can't. Next one. And well, that was a bad example. That's really too much. Anyway, but you start with some matching. Then you look, are there, well, for instance, let me just draw more edges here that we didn't take into matching. So there are some unmatched nodes on the left. Okay. Now I look if I can find alternating paths in my graph. Alternating path is a path that alternates between edges in the matching, not in the matching, in the matching, not in the matching, and so on. Okay, so this one is in the matching, this one is not in the matching. So this is an alternating path. Right? Now, such a path would be called augmenting if it starts and ends with an unmatched node. So we have a node, an edge which is not in the matching, then an edge which is in the matching, not in, not in. So if I have such a path, then obviously I can change the matching and have more, I can increase the number of matched nodes by one. So I will take now this one, and this one, and this one in the matching and exclude those. And so the algorithm proceeds until we don't have a plenty paths. This way we find maximum matching. Okay. So that's a centralized mechanism to find an optimal size matching by particular. But we are, for the moment, interested in the case where our boys and girls have preferences. Not just acceptable mates on the other side, but actually they would tell us who is their favorite, who is their a little bit less favorite, and so on, and what is favorite. So we have, as before, have boys and girls, and each of them come up with the full rank of the opposite gender side. So it's not easy to rank everyone, but assume that it's been done. Okay. So the green girl, for instance, like the blue boy the most, then the red guy, then the green guy, and so on. Which one has the others? And your job as a matchmaker is to find a matching and that would pair every boy and girl in this graph. So you have to create n couples, and this seems not be easy either. Why is not? Because if you have, like, you can come up with some matching, right? But you may have, since we have all girls and all boys ranking, all mates on the other side, so everyone is acceptable. It's just not as liked as someone else. So you may have a boy and a girl in your matching, in your initial matching, that like each other more than their current partners in the matching that you proposed to them. So what can they do? We would call them blocking pair. What can this blocking pair do? They can leave their partners and get together, right? And you don't get recognition for making this match. So you probably would like to avoid those situations where you have two matched to someone they like less than each other. And this is the notion of a stable matching. So a stable matching would be a matching that does not have any blocking pairs. So in fact, so it seems to be difficult to come up with such a thing. Mathematically speaking, no, it's good. First of all, such a thing always does exist. And more or less, and moreover, you actually can find it in poly type. And the algorithm, so the algorithm was proposed by Gale and Shapley, and it's the same Shapley that we heard about in cooperative games. By the way, for this result, for the resultant matching, it got Nobel Prize just last year or 2 weeks ago. It's very recent. It was between Alan Roth, who is he used to be a professor in Harvard, now he's in Stanford, and he's done a lot in matching theory and key exchange. He's currently living and working person, and Lloyd Chaplin from two of them. So there is an algorithm that does it in polynomial time, and in fact, it sort of, you know, mimics the human behavior. You can call it a proposal reject algorithm, and it proceeds as follows. So in the beginning of each round, there will be 2 rounds, perhaps that every boy who is currently single, he proposes to his favorite girl that he still didn't delete from his list. So if he goes there, then the girl looks at all her new proposals. She may have a few at the same round. She looks at all those, and she looks also at the current mate that, if she has one, and she picks the best of those. Okay? Now, all those guys from these new proposals and the current partner, if some of them is rejected, they would delete, forget about that girl forever. So they delete her from their list. This is one round. The next round repeats until no boy is rejected, no more rejects. Shall we? Okay, let's run it later. Let's first talk about some problems. And there are many beautiful things. Yeah. First of all, everybody gets married. Well, but under the assumptions we gave from the beginning, yeah, that's the same number of boys and the same number of girls. Everyone is heterosexual. Everyone has the full rank of everyone, so everyone is acceptable, even not equally liked, right? So this is not the ideal marriage market. So we know that there are more girls than boys on the planet, and not everyone is happy. So why is that true? Why everyone indeed gets married? So first we see that once a girl gets a proposal, she's always married. Maybe not to the same guy all the time, but she never gets single again, right? So that's one thing to remember. Next thing, that a boy can be single because boys propose, right? From the very first round, they propose to their favorite girl. So a boy is single only if he's got rejected. No other way. So if he was accepted, that's it. Well, but he can be rejected later. Right? So he is single only if there was a reject. So now assume that there was a guy who is not married, so there must be a single girl. Look at that single girl. So that girl must have been proposed by that guy at some point in the algorithm, right? So that means that she has to be married by this point. So if she was proposed once by someone, she has to be married to someone, and she's single. A contradiction, so everyone gets married. Beautiful. Now, more than that, the outcome of this algorithm, which is very simple, you would agree, is a stable match. Why is that true? So assume otherwise, the matching is not stable, so we must have a lock-in pair, B and G, or B and the girl G. So suppose that B is married to some girl G0 who he likes less than G, and G is married to some B0 whom she likes less than B. What would that mean? That means that B must have proposed to G at some point, because he goes from his favorite down his list. If he is now married to someone else who he likes less, then G was somewhere on the way and she rejected him, right? So if she rejected him, that could only happen if she had a proposal from someone that she liked better than B, right? But now she is married, but the girls, what happened to the girls? Like they get some proposal, then they change a partner only if they get a better proposal. So girls only go up with the algorithm. So if she was proposed by B and she rejected B, she had someone better than B, and now she is married to B0 who is worse than B. Can't be the truth. Okay, so we've got a contradiction. So indeed it is a stable match. And it also takes not that long to achieve. Indeed, at every round, except from the very last one where we have no more rejects, the boy crosses a goal off the list. So the boy that was rejected crosses a goal from the list, and then how many crosses can there be? And -1 for each boy. One goal, next goal, until the last one. And there are n boys, so we have n multiplied by n-1, and the last round plus 1. Okay, so no more than n squared. Pretty fast. An easy exercise. How long will it take for the algorithm to run if all the boys have different top choices, different favorite goals? One round, right? They propose to their favorite goals. Every girl has just one proposal they accept, the first proposal that you accept, and that's it. No changes. What happens if they have, if all the boys have exactly same lists, preferences? So in the first round, what happens? They all go to the same goal. What does she do? She picks the best one. N-1 boys rejected. Right? What do they do next round? They go again to the same goal, the second best in their list. They have all the same, they're all as ones. Okay, only one of them is accepted, the best one given her preferences. So how long will it take? Exactly n rounds, right? The number of goals. Now, what do you think? Who does better in this algorithm, boys or girls? Why? Because it's always the case.
It's always like that.
So on one hand side, you could tell maybe that girls are those who made decision here, right? So they decide whether to accept or reject. So they probably would do better. But on the other hand, you're right. Boys actually start with their top choices, and they only sort of compromise if they got rejected. And girls actually may start from the very bottom, and if they're lucky to get more proposals, they would improve their situation. And it's not just better or worse, it's actually quite bad and quite good. So let us put it formally. So if we look at the set of all stable matchings, we know that it's not empty. We know that a stable matching always does exist. And for every person, we would look at the set, call it the realm of possibility, the set of all mates that he or she can be paired with in a stable matching, some stable matching. Okay. Now, the optimal match for a person would be his favorite from his realm of possibility, and the decimal one would be the least favorite of the same set. now what happens is, the algorithm pairs every boy with his optimal match and every girl with her passive match. So the best possible and the worst possible. Of course, if the girls would propose, the situation would be the other way around. So this shows that it probably pays out to be, active and aggressive on whatever marriage market, and don't mind a few rejection at the beginning. You would come up with something better than if you just wait. Let's do an example. Let's just run the algorithm. We have girls, Emmy, Beth, Farah, Dana, Eve. Enough. And we have boys. A, B, C, D, E, F, and A, Fred. Al, Ian, Jake. Let's come up with preferences. Emmy. Any. F, G, without loss of generality, she's the first one. Hal, Ian, J. Beth also likes Frank, then she likes Jake, maybe, then George, then Ian, then Hal. Kara, Jake, Hal, George, Ian, Frank, Ian, Frank, George, Jake, L, George, Ian, Jake. Who's left? Fred. Right. Fred. Let's make them unhappy. So no Emmy or Beth. Kara. Dana. Okay. Abby. Eve. Poor Beth. She's gonna suffer, George. Okay, Annie. Dana, Amy, Eve, Kara, Beth. Okay. How loud's Beth? Amy again. Kara, Dana, Eve, Dana, Beth, Kara, Amy. For you. Amy, Beth, Dana, Kara. So what happens in the first round? Say, is there only one round? Bad preferences. All right, yeah. Let's make some drama. Okay. So Fred and George go to Kara. So let's do accept, reject. Okay. Fred and George go to Kara. She accepts George. So George, Fred. What happens? No Kara. And Hal goes to Beth. She doesn't like him, but what can she do? No one else is available. And Ian and Jake go to Eve, and she accepts Ian. and Jake is rejected, and he forgets about it. So now we have Fred and Jake to proceed to the next round, right? So in the next round, okay, but again, we won't have too many of them. Okay, they go to different goals now, right? Fred goes to Dana and gets accepted, right? And Jake goes to Beth. Now Beth, what does she do? She accepts Jake and rejects Hal. Hal says goodbye. Now, who is unmatched of the boys? Only Hal, right? So he goes to Amy, who is unmarried. Okay, happy. Okay, so 3 rounds, and she gets out. So we got Pam, Hal, and Amy. Who else? Beth is with Jake. And Cara is with George, is she? And Dana is with Fred, and Eve is with Eve. What happens if girls propose first? Okay, let's see if indeed they would do better. Maybe in this example they won't, but they shouldn't do both of these. That side. If okay, Cara goes to Jake, accepted. Dana goes to Ian, accepted, and Eve goes to Hal and gets accepted, while Amy and Beth both go to Fred, and he says Amy, and Beth is rejected, so she goes to Jake. All right, same thing, is it? No. Okay, so now we have Beth going to Jake, but Jake is married, of course. So she goes to Jake, who is married to Eve. No, Jake is married to Cara, but he does prefer Beth. So he accepts Beth, and he rejects Cara, and she goes where? Hal. Wait, first of all, she forgets about him. And then she goes to Hal, who is married now to... Oh my God. Eve. Oh. And Hal hates Eve, luckily. So, yeah, he accepts... What's going on? Cara, thank you. And he rejects Eve. And Eve says bye, and she goes to George, but George is... Oh, here, oh, nice. Okay, so, congratulations. Is it the same marriage in the end?
No.
No, Amy is now married to Fred, is she?
Yeah.
Yeah, and she was married to Hal, and indeed she likes Fred more than Hal, so when girls propose they do better. And you can check for everything. Okay, so let's have a little, maybe